Okay, that's about what we can learn from psychology and neuroscience. Let's look where our robots really have to work with. So there are a lot of sensors that are available. We're going to a lot of big tables. Part are mechanical, part are based on photoreceptors, part are sensitive to changes in chemistry. And you have to classify because this is really a big class of different sensing. So the main class that you can describe is the first one is the interoception. So everything that you perceive from your inner state. And strange enough, we have a lot of sensors in our body, but we only feel mostly none of it. Only when there is something wrong with it. When you're drunk, then you feel your inner state, and otherwise you're not that much aware of it. You have the proprioception. That's the position of yourself in the world, including your body and your body parts, and you're really with it sensitive for that. If you put a rubber hand in front of you and you hit it with a knife, then it feels like with it your real body is hit. And then everything that you perceive from your environment, the exteroception. And we will see examples from all of that. So what a lot of internal sensors we see. These are the most common ones for mobile robots. The first one is dead reckoning. That's counting how many turns your wheels make. GPS to know where you are in the world. Obstacles are seen by ultrasound, but most of the detail you can get from computer vision and laser scans. And we will go a little bit deeper into each of those. So if we were to classify everything as internal or external, then we see that tactile sensors are really important. Part of them are bumpers if you're hitting something, but think of animals on whispers, and that are really great ways to feel an obstacle if you're quite close to it. Most of the robots have wheels, or even if you move an arm, or you do that by gears. So you have a lot of encoders that can feel the movement of those different gears. You have heading sensors, for instance a compass, but also gyroscopes that you know which way you're heading. You have a lot of sensors that try to find your position from external beacons. The most well-known, but actually doesn't exist that long, is GPS. That only became popular after the first Gulf War, when the American army didn't have enough military GPS signals and opened it up for civil applications. And after that, all the transport and all the robots were so relying on GPS, and now you cannot find any address anymore without your Google Maps that relies heavily on GPS. If you want to see obstacles from quite afar, then the best way is do active ranging. That means that you send a signal and you look for the echo, how long it takes to get that back. And the submarines use ultrasound with echolocation to know how far the seabed is under them and where the different other ships are going. But you can also use lasers or radar to detect all obstacles around you. It's not only important to know where the obstacles are, but also how fast you go. Radar can also be used to meet speed. That's where you get your speed tickets from. And the most common now, because thanks to your telephone, it really gets cheap, is vision. And that's also the sensor we rely on as humans mostly. So, we give examples how the most important of those sensors look like. The encoders is something with it you well know. Part of them with it in the old mouses you had roller balls where you could see with it the ball rolling when you put it over your table. When I was a student, we with it went to an arcade. There, the first time you had a game that you have to go to a 3D world where there's a really big ball on the table that you have to give a swing, and how further you came on levels, how fast you had to stop it and give it a turn. So on the end of my the holidays, I really had open with it stems from all the spinning and stopping of those balls, and they recorded all those movements with encoders. So how does it work? That's comparable if you go to the shopping. There you have the barcodes. The barcodes is put on a circle on the axis, and you see how many times a different pattern on or off goes along a laser scan with a diode, and based on that you can estimate the angle that that axis has driven. And if you aggregate that, then you can get a quite reliable estimate of the distance that wheel has traveled. So heading sensors, most of them are well known, are compasses, but they are not that reliable. First, depending on where you are and what sort of soil you have, you can have quite large disturbances in the magnetic field. Even the magnetic North Pole is moving every year a small distance, so that's not constant. And you can have a lot of disturbances if you're indoor by all the equipment that's around you. So currently most of the heading is done by gyroscopes. Previously it were sort of tilt sensors with small balls that were rolling into it. But now everything is done optically, and you can very lightweight get a quite good estimate of your heading. The downside of it is this is all the information that is aggregated. That means that slowly an error builds up, and at a certain time you have to recalibrate it again against an external sensor. So the EMU are with it the sensors that combine the speed measurements with the acceleration measurements and build up a quite reliable estimate of your position, and do it with Kalman filters, and that gives a quite reliable estimate. But still, the error builds up, so at a certain moment you have to build up against the beacons. If you're in an industrial environment, you can do that by putting reflectors in the corners of the room, and that's actually also the same way that they reliably measured the distance to the moon, because the first astronauts put reflectors on the moon, and you can point with your laser to the moon, get a reflection back, and measure how big the distance to the moon is. And you can do the same in the rooms. Actually, I worked on a research project where we put a sort of pseudo-satellites in the building. They said that they were satellites in the sky, but actually they were satellites hanging on ceiling, and they used satellites that are on the other side of the Earth, so in Australia, and in that way you have your GPS working indoors. The only downside of it is that all those small pseudo-satellites need a very well-calibrated clock, So you needed to put a fiber network between them to get the all synchronized. So the satellites that are circling around the Earth all have that atomic clock on it, because they all send a small signal. But if you have to calculate the travel distance, you have to know when they were sent. So if you see 4 satellites, you can get a quite good estimate of the time. And in principle, you can get a quite good estimate. I say quite good because every time the systems should be recalibrated on the path they're actually flying around the Earth. At a certain time, one of the satellites above America hit a burst of the atmosphere and started to descend before they could switch it off. So it was crashing onto Earth and keep on functioning and saying with it, sending its signal. So that was the largest error with GPS there was ever with it sent, because if you rely on that satellite that was crashing, you get an error of a few kilometers. Because it was tumbling, they couldn't switch it off fast enough. So for a few minutes, you can have huge estimates. If you're normally operating, the biggest difficulty is if you are in urban canyons where you don't see 4 satellites, and then you have less reliable signal. So range sensors, you have very different ways. Very popular in the 80s was sonar, where you sent out with a microphone a signal, and with it you listen with it for the return signal. After that, the laser scans came up. They can give far more detailed information and are accurate in half centimeter. Unfortunately, they mainly give a signal in 2D. If you want to have 3D, then you really have a 10 times as expensive sensor. Before with it, there was a lot work on time-of-flight cameras, but later on by Microsoft and Kinect, it was solved by structured light. So in principle, if you use ultrasonic sensor, you use the same system as a badge. You send a sound with a certain bit pattern out, and you listen for the reflection. What you see is that most signal is sent in a certain direction, but you see some side lobes on the side. In principle, because this is a logarithmic scale, they are quite weak, at least 100 times as less strong as the main signal. But if the main signal hits some absorbent surface, as a couch, and the side lobe hits something of metal, what reflects sounds very well, then you can still be more than 30 degrees off. So if you are in a room, as here on the lower right, then you can see that you often see on the bottom the walls quite well, but in the corners and in other places you can have quite wrong measurements. And that's partly because the sound is traveling around the corners and give quite long disturbances, specular reflections. So most of the cars that are now shown as self-driving rely on the measurements of laser scans. We have several of them in our lab. But if you want to drive, as you see on this smart, that is made smarter, you see that you need several of those laser scans. You can, with the circle, count 4 of those to get a reliable measurement of your environment and know where to drive. In principle, the laser range sensors use the same principle. They send out a laser beam with a certain phase, and depending on the signal back, they see what the shift in the phase is and can calculate the distance traveled of those signals. And you can measure with it obstacles up to 60, 80 meters and with quite a high accuracy. So if you measure a room like this, you get really with it nice estimates of the walls. Here with it, not only the measurements are given, but also the uncertainty that you have, but you can create quite high accurate maps of your surrounding. So previously you had a lot of work on with it, range cameras that give 3D measurements. Currently you have a lot of sensors that give disparity with it quite reliable, and that's great to recognize a chair if you do the artificial coloring on distance, as you see on the right. So we do a lot with vision, but our vision system is not that high resolution or that fast. But it's really good in interpretation. If you see the drawing on the left, you directly with it recognize some playing children in it. But that's because everybody is fond of playing children. And on the right you see some dots, but once you have seen the dog in this image, you always with it get it back. Well, it's quite impossible with it to recognize these sort of things out of the clues. And it becomes because we know what we're looking for and what we're sensitive for, so that's we're really steered by our expectations. So that's really difficult for in robotics to get the same awareness with your vision with it as we humans do. In principle, you observe everything like a camera obscura. So you put everything that you see in 3D, you project it on a 2D image, and then you start to trying to convert that into objects. And our brain is very good in it, and we're getting better and better with vision for robotics. So in principle, we can measure some distance with cameras, and a lot of stereo vision approaches have been done. But also our own stereo vision is not that good. It's very handy if you have to pick something in front of your nose, but really estimated distances with it further than your arms. You does it on size and not really on disparity between your left and your right arm, because everything farther than your arms has the same distance. And the same is true if you do stereo vision with robots. You really need a huge baseline to really with it recognize something from afar. You can do it, but then you have to move your robot, and that's structure for motion. So what really is the latest approach, and that's things that are done in Zurich, is that instead of every time getting a full image with it, you only they made a sensor that is only sensitive to movement, so it only sends the pixels that are changing. And that means that you can get really sensitive to moving edges, and that's quite realistic also how the human brain works. And in that sense you can make sensors that are great for drones that move very fast. The only difficulty is that you need a complete new library of recognizing software to get objects out of this sort of sensors. But that's the way to go, because that's the way we humans do it. And if we have the same agility of the robots, we should work on that. Is it really how the human vision works? And if we look to the human vision, we see that we have the eyeballs, and we have more than retina with more than 130 million photoreceptors on it. Part of them sensitive to color, part of them only sensitive to black and white. And everything that we see is sent via the nerves to the brain. And then we're starting to work to get that operating. And what we see is those sensors that are only sensitive to changes. You can starting to aggregate all those signals that are given, and you can recreate the images that you built from that camera, so you recognize your keyboard or your surroundings. So what's the difference? If you have a circle with one dot on it, and you have a standard camera, you get every time the big white circle with the dot on it, and on the DVS you only see the moving dot. But instead of getting it frame by frame, you get it in a much higher frequency. And if you have it, then you can start looking for correspondence, that you can see edges that you see backwards. And we see here two images. For you, maybe it looks quite the same, but if you look in the chair in the front, you see that actually you shifted more than half a meter. And we can easily recognize the same scene because different parts of the image you really can correspond. And a lot of the things that we've done in computer vision is finding features that are insensitive both to scaling and movement, and that you can find back if you have two a bit similar images but slightly moved. So if you have that, then you can try to reconstruct everything that you see with triangulation, because you know what's in the left and in the right image what's the same, and then you can create images from somebody that's standing in front of a screen, and you clearly can see the shadow where both cameras could not look. So we are in principle hunters. We are looking mainly with it straight ahead. A lot of animals that are prey have to look everywhere around them. So we also built cameras that have much wider field of view. Some of them even has a 360 field of view, and it is great for robotics because you see the obstacles everywhere around you. The problem is if you have such a sensor, you can do that with having a camera that's look to a reflecting mirror, and that means that you can see the world everywhere, but quite deformed. But what you can do is rewrap that image to a panoramic image, and then you can see everything surrounding you. Not everything with the same resolution, but still something that you can recognize better. Okay, that's everything that I want to tell about real robot sensors. Then how you're going to use them in robotics. What you can try to do that is to combine all those sensor streams with the active processes that you have, and each of those perceptual activities are combined with a control task of your robot. So what you do is that you start both a perceptual sensor and an actuator module and couple those two to control your robot. And in the different behavioral languages, we have seen how you can define such schemes formally, and in those languages you can also indicate when such a scheme gets active, and you can threshold that by giving a certain uncertainty, and if the uncertainty drops to a certain level, then some of those perceptual schemes can start active and start sending signals to their actuation schemes. So what sort of perceptual schemes you can think of? So one of the important concepts where you start looking for in your sensors is the path you should drive on. You can do that by looking for the edges. What's then important is if you are in path, you have the path, the point on the horizon where the path ends. So that's the point where you should drive to. What's nice is you can see edges, but you can also see the color and the texture of the path you're driving on. But if you are driving in outside with shadows, then you have to learn that the color and the texture of a path can change while driving. If you know the edges of where you are currently driving on now in shadow, and if you know the edges and that they are comparable, the lines continue in the sunlight, then you can relearn the color and the texture of the path in the future. And actually, Sebastian Trun was the robot that won the first DARPA challenge with driving autonomously. Actually did that nicely by, at the moment that he had such a shadow threshold, he reduced the speed, learned the new path, and then drove on further. And that was actually using a stay-on-path sensor. So, visual routines are based on Marsh theory of vision. So that's one of the big guys of artificial intelligence. What they see is that we know each object by something that likes to look a primary sketch. That's why we have cartoons. With some drawings, you can easily characterize certain objects. And purely going on edges, textures, that's okay. But in principle, you want to go to a 2.5D sketch. And it means that those edges and textures define the surfaces, but you know very well what the orientations are of those surfaces and what's inside and what's outside. And that's far easier than going to full 3D models where you define with it volumes. In the most cases, 2.5 sketches with surfaces with orientations are enough. So that scheme with it is used with it by the robot Ulysses, where they have different perceptual routines. So we find those perceptual routines in nearly every behavior-based robots that are schemes like find the current lane, find the car next to you, find the sign on the road, find the intersections, mark with it the lane adjacent. So that's the place where you should not come because there's traffic coming towards you. And all that sort of things that every driving robot should know. So A lot of it is giving continuous with it signals, but you also have certain perceptual classes that are more binary, and that's where you have to divide some objects into binary classes, obstacle or non-obstacle, or road or non-road. And if you can classify what the different objects that you see around you, which is the road and which is the grass or the non-road, then with it you can make your life much easier. The last part from Harshville is lightweight vision, and there it's not to make a percept for each object in general, but for special perceptual processes. So you're actually looking for a light floor, and you have a sensor that's specialized for that. A sensor that is only with it sensitive is the wall ahead and doesn't disturb itself from everything that is on the side. And perceptual scheme that's just concentrating on the vanishing point. That's the point where you should drive. And in that way, by keeping it simple and not building a full object with all the parameters that you have, you can make your life much easier, because you can have all those different things running next to each other and combine all this information on the end. So that brings me to how you could combine the different percepts that each behavior needs. You can with it create specialized percepts for each of the behaviors. Then you do with it vision, where you really separate everything. The downside is that you can do a lot of things double. You don't make use efficiently of things that you can reuse. You can do fusion, where you have different clues from different percepts that in principle look at the same object. And with the confidence they all have, you can combine it with having one virtual sensor that combines all those percepts. That's fusion. And as last, you have fashion. As you know, fashion always changes every a year, and that you have different percepts that can feed the same behavior. And depending on the circumstances or the time or the place that you have in the mission, you select the one that is appropriate for that. So you have a night vision and day vision, and you specialize each of the percepts on the different circumstances. Okay, until now we all have seen the sensors as quite passive. So you have a stream of data and you do your best to get the best of it. For robotics, that's not completely true. Partly also our own sensors, if we go outside, but then our ears is closing and we adjust to the sun. And that's also things that can be done. You can change the zoom and the focus of your camera. If you have a pan tilt, you can even redirect your camera to certain points. And that's great if you see there is an object with a red edge around it. Then there's a big chance that you have a traffic sign there, and you can zoom in your camera to actually look what sort of a message is in a traffic sign, and if it's really a traffic sign. Okay. What's further with it is important is you can extract features from images reliable without the use of models. All the models that you have are in the features itself, and which feature you use, you can actually with it learn with it if you know how valuable they are. You can use that as a reinforcement signal to your sensors to learn what's important. Further, what's important, what we said, when you're driving around, you need sometimes to have make decisions, say on gateways where you have to go left or right. So it's nice if you can recognize objects on that positions. So what you need, what you want is really discriminative objects to recognize, but that are visible from quite a large distance, but are not that common that you see them everywhere. And it's great if you have frames of reference available to see what the same object is. Say the McDonald's sign is not the same as the other one because it's on a different location. So, what is an active vision architecture? In principle, you have a camera, and that gives a number of low-level image features. You try to track those features along with when you're driving around. Some of them you will lose. Other ones you will gain. How do you gain them? You every time have proposals what are also interesting features to look for, and you can keep a sort of list of what are attractive features that should be tracked. And if you can track them reliable for certain frames, then you can really use those features also to estimate what your motion of your camera is, and you can feed that to your robot. So, do we still need models to build from the world from your perception? What you see is, in principle, you have an architecture where there's a direct coupling from the perception and the behaviors, but what we also have seen that a lot of those information stream can be tapped and can be used to build up models of the world where you also have interpretation, what sort of objects you have seen. And with that long-term memory, you can also do predictions, and you can send that again as virtual sensors, models as advice to the behavior again to make smarter decisions. So it's not an or, but it's something like and you can do two things at the same time. Both have a short-term and a long-term memory. And that's also reflected in this slide, where you have different hierarchies, and each has its own time frames. Each has a history where it builds up and learns how to process raw data, how to maintain features, how to look on objects that start to have correspondence with things in the world, like doors, humans, soda bottles. And on the end, you combine all those objects to places, situations, and then you can decide what to do there. So, to wrap up the whole story, we have seen a rich variety of sensors, and that's the ones that are available to robots. Nature is even richer. You can have far more sensors in the animal kingdom. Most of them have a clear operational model where to apply it and where not, and how accurate they are. but you need some experience to know what sensor to use when. And nature has the whole evolution to make that selection. But as a robotic engineer, you have to do it yourself. What you see is that you often have to fuse information coming from different places and different times to get a full view of your local surroundings. So that's something that you should be able to do, to combine information from different sensor streams. But if you can do that, then you can quite reliable navigate through the world. And in that sense, vision is the sensor that's one of the cheapest and also gives the richest information. But it's quite also one of the most difficult one to process and to make sense of everything that you see. Okay, thank you for your attention and hope to see you next time.